So welcome everyone. Thanks for joining in person and online. So this is the first seminar back in Maths in the Life Sciences / Northwest Biology series of data science. That was it, Mathematical Biology and Data Science series, where we welcome Liverpool and LJMU colleagues online as well. So this is the first semester back first seminar back this semester, and we're very lucky to have Alex Hening visiting us all the way from Texas A&M. So he happens to have some family nearby, and very opportunistically for us, we managed to bag him for a seminar right at the start of the semester. So Alex did his PhD at Berkeley, then moved over to the UK, did postdocs at Oxford and Imperial, and then back over to the US, where he's now, say, at Texas A&M in a sort of tenure track sort of position, right? Great. And today, Alex is going to be talking about modern coexistence theory and beyond. So over to you.
Thank you for that kind introduction, and thank you for having me here. It's a pleasure. So I'll be telling you a bit about my work in this field of population dynamics, and more specifically, what ecologists call modern coexistence theory. Okay, so in biology, people care about when things go extinct and when they persist. So a long-standing question is trying to figure out when species coexist in an ecosystem. Usually you have very complicated interactions, you have predator-prey behavior, you have mutualism, you have competition for resources. The question is, how can you model this mathematically? And what's the long-term behavior of the system? So what do we need to take into account if we want to have a realistic model? Well, we want to take the species interactions into account, of course, and then we also have to take into account that the environment itself is inherently stochastic, right? So there will always be environmental fluctuations which we cannot predict, and these environmental fluctuations will change the species, the way the species interact. It will change the growth rates, the death rates, the competition rates. So we need some way to quantify this randomness. And modern coexistence theory is one of the most successful theories which tackles these issues. It's been developed by Peter Chesson in the late 80s and is very widely used by ecologists. Okay, now what are some of the shortcomings of MCT, or modern coexistence theory? Well, they can only treat small environmental fluctuations. Okay, and usually in reality, you want to be able to capture also larger environmental fluctuations. And as a mathematician, I care about rigorous math results, so they can only prove rigorous results when there are two species. Of course, any ecosystem will have tens of species, if not hundreds. Also, they can only prove results for persistence. They don't have any results about when species go extinct. Okay. However, Chesson and Ellner conjectured in the late 80s that the results should hold for any number of species, and one should also be able to prove results for extinction. Now, since they conjectured that in the 80s, there has been progress, but only in specific settings. So people can treat a specific system with 3 species or one with 4 and so on, but we wanted to come up with a theory which works in general. So that's been one of the main directions of my research. We wanted to generalize this modern coexistence theory. We wanted it to include large environmental fluctuations, and we wanted rigorous results which work for any number of species. And we wanted to also know exactly which species persist and which go extinct. Okay, so we were able to provide a complete account which can include all these things we wanted included, right? Okay, so let's get to the results, but let's start with the toy example first. So we have the simplest deterministic model of population growth. We just have exponential growth. So we have a differential equation, right? X is the population abundance in time t. And it's just given by this, right? The per capita growth rate of the population is equal to R, a fixed number. Of course, it's trivial. You can solve it analytically. It's just exponential. And what's important for us is that the limit of the log of x divided by t as time goes to infinity is, of course, R. So R captures the long-term behavior, right? If R is positive, it blows up. If R is negative, it goes extinct. Okay, now there are multiple ways in which one can include noise. One way is to assume that the growth rate R is not a constant, but it's given by something like this. So it's actually an average R plus white noise fluctuations around that average. And then the previous differential equation now becomes something called a stochastic differential equation. So you have this noise term here in red, where B is a Brownian motion, which is a nice continuous stochastic process. Okay, so we were able to include noise by adding this so-called white noise term. And what's important is that it looks like X, the density, times the Brownian motion. So in a way, it's linear in the noise. So, okay, now you can use Ito's lemma because you still look at the same. You still want to say to see what happens with the log divided by t. And if you use Ito's lemma and compute log x over t and take the limit, you get a correction term. It's not R anymore. It's R minus sigma squared over 2. So it's exactly 1 minus 1/2 times the variance of the noise. So this here tells us in a way that noise is bad because it always decreases your growth. Then you're able to show that if this so-called stochastic growth rate is negative, the population goes extinct almost surely. If it's positive, it blows up. Well, it's not realistic to have the population blows up, but this happens just like in the deterministics. I think it happens because we didn't have any type of competition for resources. So it's easy to amend this. You just add a term here in the drift, which looks like minus kx multiplied by that x, so it's minus kx squared, which just says that, well, if the species densities increases, there's a very strong competition, and then you get a strong drift towards 0. So it's not good to be at a very high density because then there are not enough resources. Okay, so now this is nonlinear now, this stochastic differential equation, but you can show that the same stochastic growth rate, so this R minus sigma squared over 2, determines the long-term behavior. So namely, if it's negative, population goes extinct. If it's positive, now it doesn't blow up, but it converges to some type of random equilibrium. So it actually converges to something called an invariant probability ratio or a stationary distribution. Okay, so the key thing is that this R minus sigma squared completely determines the long-term behavior. Okay, so now that we looked at the toy example, we can look at the general theory. So we have an ecosystem with n species, which we capture their abundances or their densities through this vector here, x1 through xn. And then the deterministic dynamics is just given by a system of differential equations. If we just look at species I, we have the per capita growth rate of species I is given by fi, and it can depend non-linearly on all the other species, right? So this is extremely general. And then we do the same thing, namely we add noise. I will tell you about other ways of adding noise. This is just the first way. So that a system of differential equations becomes a system of stochastic differential equations. Here you have multiple Brownian motions, and the simplest thing would be just to assume that they're independent of each other. So then the question is, what can we say about this system? What determines the long-term behavior? Now, we need a way to quantify persistence because we can't just say that it converges to 0 or it doesn't converge to 0. Because when you have when you have noise, it will be the case that the densities will get close to zero and then will escape, then they will get close to zero again. So one way of quantifying persistence is saying that species xj is persistent in probability if, with high probability, it's bounded away from xh. Okay, and then if this happens for all species, you say that the species coexist. Okay, now a stronger type of coexistence is if you have some type of random equilibrium. So it will be given by something called an invariant probability measure, right? So this is the random equivalent of an attractor or of a fixed point, if you will, right? So if you have your process X and you started with this initial distribution, then the distribution always stays the same. Just like when in a deterministic setting, if you start at a fixed point, you just stay there forever. But now there are no fixed points in general. When you have noise, you're always pushed away from the fixed points. So what you'll have is a stationary distribution or invariant probability. So think of it as the random equivalent of a fixed point or of an attractor. Okay, so now I'll tell you a bit about the generalizations of those stochastic growth rates. They're called Lyapunov exponents or sometimes invasion rates. So suppose we have a subcommunity. So not all of our species are present, right? Strict subcommunity of n species, at least some species are not there. And suppose they coexist. Now the coexistence will be given by one of these random analogs of a fixed point. So they coexist, and their coexistence is determined by some invariant probability measure mu sub n. Now we have a new species I, which is introduced at a very low density. So it's given by the stochastic differential equation, but we want to do something like linearizing around an equilibrium. But now it will be linearizing the system around this subcommunity. So it's like linearizing around the stationary distribution. That's what we're doing. So what we're taking the log of xi, dividing it by t, and we get this term here. And the minus gi squared over 2 comes from Ito's lemma, because when you do stochastic calculus, it's not exactly the same as ordinary calculus. You get some correction terms because of the Brownian motion. So now we want to, at least intuitively, take the limit of this as t goes to infinity. This term goes to 0. You can show that if gi is well behaved, doesn't grow too fast, this term also goes to 0. And the only term that matters is this red term. So one can show that this term is approximated well by just an integral average, where you take the average. So this is exactly the stochastic growth rate, but you average it according to the stationary distribution of the resident population. So again, it's just the equivalent of you have a fixed point in the deterministic system. What happens if you move a tiny bit away from that fixed point? You want to see if you tend to get attracted back to the fixed point or repelled. You do the same thing, but you do it with these invariant probability measures or stationary distribution. So this is just an average growth rate, where you average over the community you're trying to invade. Okay, so so I said before, the other two terms, so these two terms go to 0, and this so-called invasion rate will basically tell you what happens with species I when it tries to invade at the low density. Does it tend to grow, or does it tend to go extinct? And note that in that example we started with, if you just look at that example and you take the simplest possible invariant measure, it will be the Dirac mass at 0. So that's the invariant measure where all the species are extinct, right? That's always going to be an invariant measure here, because if everything is extinct, you start there, you stay extinct, nothing gets resurrected. So if you just compute that Lyapunov exponent, you just get what we had there initially, right? Mu minus sigma squared over 2. But for higher dimensional or more complicated systems, sometimes it won't be as easy to compute these invariant measures, these Lyapunov exponents. Okay, so intuitively, if this invasion rate is negative, means species I tends to decrease when you introduce it to the low density. When it's positive, means species I tends to increase when you introduce it at the locals. Okay, and now we have a general result for coexistence. What does it say? So suppose that for any subcommunity of species, strict subcommunities, so not all are present, if the subcommunity has an invariant probability measure, we assume that there exists at least one species which has a positive invasion, right? So at least one species which is not in that community can invade it. If that happens for all subcommunities, then the end species coexist. So what's the intuition? You have these subcommunities which live on the boundary, right? Because the subcommunities always have some species missing. And whenever your process gets close to the boundary, it feels either attracted or repelled by these subcommunities, according to these Lyapunov exponents or invasion. So this here just tells you whenever you get close to the boundary, you get pushed away in at least one direction. That's why you cannot go extinct, because whenever it gets close to the boundary, it gets pushed away from the boundary. So that's the general coexistence result. And now I want to tell you something about conjecture due to Palis, right? We always in dynamical systems, which get used everywhere, you always care about the classifying their long-term behavior, right? So Palis conjecture for differential equations that typically there's a finite number of stationary distributions we were talking about, which fully characterize the long-term behavior. So just by looking at these stationary distributions, we should be able to say everything that happens. And this is an open question in many cases, even for the deterministic systems, but we are able to prove it for three species stochastic differential equations. We're able to prove Palis's conjecture. So the long-term behavior is just determined by a finite number of these invariant probability measures. And many people frown when we say that it's just for three species. But actually, this is not true for the deterministic system. So in the deterministic case, when there's no noise, Palis's conjecture is still open. You cannot show that the long-term behavior is fully determined by these invariant measures. So it's a big deal that we could do it even for three species. Okay, so what can happen in these systems? I'll tell you what the classification is. All right, so you have three interacting species. One thing that can happen is they converge to a stationary distribution. So this is a simulation here. You converge to something random, but which is away from the boundary. It doesn't put mass on the boundary. The second type of behavior is you converge to something which just supports species one. So species 2 and 3 go extinct, only species 1 persists. So that's why you converge to this axis here, the x1 axis. Or there's something like this, where you can either converge to the x1 axis or to the other axis. So if you start from here, there's a certain probability you converge here, and species 1 persists, the other two species go extinct. 1 minus that probability that you converge here. So one of these two things will happen. It cannot, nothing else.
So in what technical sense do you not converge on everything being zero very long term, if it's a Lotka-Volterra type system?
Yeah. So here, what I mean here, the convergence just means that as time goes to infinity, because we can prove that for these systems, you can never converge in finite time to the boundary because of how we have the noise. The noise looks like x times dB. If the noise would look like square root of x, which usually is called demographic stochasticity, then you converge with probability 1 in finite time. But when it looks like x times dB, we can show that the interior is an invariant set. So you can only converge as time goes asymptotically, in a way. So I don't know if that's
Yeah. So in what sense do you come? So something acting like that, just because your increments are log null, right? So you don't have any mass in. Because so the intuition is you're doing Gaussian motion, Gaussian in log space, so you can't You can't go to negative infinity.
Exactly.
In log space.
Yeah. So then, I mean, you can see most of the things are intuitive, or you have a setting where you converge to one of the three axes. I'll go quicker. Or you converge to something which supports both x1 and x2. So x1 and x2 persist and x3 goes extinct. Or there's something where you either converge to this axis or you converge to this space. You'll see that the last one is more interesting. Here you converge to one of two faces, this face or this one. Or you converge to one of the three faces, and we show that all of these are possible. And then the last one is the most interesting. You don't converge to any face or any axis. What you actually converge to is a convex combination of single species. So it looks like rock, paper, scissors. People might have seen that type of dynamics. So what happens is, it looks like you're converging to x1, but x1 is defeated by x2. So from here, it actually starts going here. Then it looks like x2 is winning, but x2 is beaten by x3. So then it moves here. So it keeps cycling between these. So it looks like a heteroclinic cycle in the deterministic setting. Actually, you get these types of behaviors in nature. There are these three types of lizards. Male lizards, which compete for females, and you have this rock, paper, scissors type of dynamics because you have an aggressive lizard, which gets beaten by the furtive lizard, because this one acts as a female. So the aggressive one cannot tell that one is a male. And the furtive lizard is beaten by the guarding lizard. This one always stays next to the female, so he knows when the furtive one comes and acts as a female. And then the guarding one is then defeated by the aggressive. So you see how whenever it looks like one of them is winning, well, then it's displaced by the other. So when does this type of rock, paper, scissors system happen? Well, so you have 6 non-negative invasion rates. You can look at those which are positive. You multiply them. So those are the ones which push you away. And you look at the ones which are negative. You multiply. If what's positive is lower than what's negative, it means you converge to the boundary. So in a way, what's pushing you away is not as strong as what's pulling you back. If the opposite happens, right? So if the positive invasion rates dominate the negative ones, then you converge to something which supports all three species. So it's an interesting type of behavior, even though you keep cycling. You either converge to the boundary in a sense, or there is some type of equilibrium where things still cycle. Okay. Now I want to tell you about different type of noise, because quite often when I talk to biologists, they don't like white noise, Brownian motion. They say it's not as intuitive, maybe. So I'll introduce this new type of noise, but it's related to something called the competitive exclusion principle, which is one of fundamental principles of ecology. What does it say? Well, Gause, Volterra, and Hardin looked at multiple species competing with each other for the same resource, and they saw that in many models, it seems that there's one winner, and all the others go extinct. Right? So one species outcompetes all the others for just that one resource. It's the best at using that resource. The others go extinct. However, now if you look at in nature, that's not always what happens. Sometimes you have multiple species on just a few resources, and they all coexist. So, for example, you get plankton. You get tens, maybe hundreds of species of plankton, all competing with each other for 2 or 3 resources, and they somehow coexist. Now, when Hutchinson saw this, he called it the paradox of the plankton, right? Because it seems to be violating this fundamental principle, right? Why are all these species of plankton surviving, even though the competitive exclusion principle says that one winner should take everything? Well, Hutchinson gave a possible explanation, right? He said that maybe there are variations in time of the environment, and maybe you don't always have the same species winning, right? Maybe one species is winning now, and then the environment changes, and the different species wins, and so on. So maybe this can facilitate coexistence. So now I'll try to show you a model of how you can get this type of coexistence. Okay, so we start again with a deterministic model. You have two species, x1 and x2. They compete for one resource R. Okay, so this is the differential equation for species one. It just says that so R is the resource. If there's no resource, species one goes extinct with rate alpha one. Again, it goes extinct infinite, infinite, right? It approaches extinction. And here, this tells me that if I have 1 unit of resource, this is how efficient it is at using up that resource. So B1 you can think of it as it measures the number of offspring per unit of resource, right? And the same thing for species two. So you have these two equations, and R will be the resource, which depends on x1 and x2. Of course, now I have to tell you what R looks like if I want to say something about the dynamics. And one assumption is that if you have this abiotic resource, it depends linearly on the densities. So there's some maximal value of the resource, R bar, and then it decreases linearly in x1 and x2. So then, if you plug this back into the previous system, you just get the Lotka-Volterra competition, right? X1 and x2, it's a competitive Lotka-Volterra system. However, there's a certain interdependency between the coefficients, right? And you can actually show that here in this system, the competitive exclusion principle holds. So only one of these two species can survive. It's impossible, even though in general, when you have just a Lotka-Volterra, of course, it's possible for both to persist. But here, there's a dependency, like I said, because we want to model just one resource, right? There's one resource. Okay, so now let's introduce some type of randomness. So I already argued why we care about randomness, that it's natural to have randomness. Yeah.
Sorry, it's in the previous slide. Isn't everything going extinct because the resource is just disappearing over time rather than getting replenished in any way?
Well, in a way, but see here, when x1 and x2 decrease, the resource gets replenished. Right? If x1 is 0, and x2 is very small, the resource is almost at the maximal capacity again.
It's like resource in use, right?
Yeah, it's used
Oh,
use as in
okay,
use.
yeah.
Yeah. So the resource never gets fully.
Okay, okay.
It's all you always have.
It's like space almost.
Yes. You can think, that's why you can even think of it as being negative. Negative just means you need to wait a long time until you get back in line because it's in use by someone else. Okay, so let me tell you about this second way of adding noise. You just switch at random between two different environments. So assume you have winter and summer, and the coefficients in your ODE change, right? Maybe the interactions are different in winter and summer. And now the randomness comes from how long the winter is, not how long the summer is. But of course, to make it work mathematically, it won't look exactly like winter and summer because these will be exponentially distributed random variables. So yeah, again, the simplest thing is you have two environments, 1 and 2. You start in environment 1, follow a differential equation in environment 1 for a random time, which will be exponential, and then you switch to the other environment. You stay and follow the differential equation in that environment for a random time, and then you switch to the other one. So you keep switching between these two environments. The randomness is just due to how long you spend in each environment. They're called piecewise deterministic Markov processes. That's the class. Okay. So then you switch to the other environment and follow. So the structure of the two systems looks the same, but the coefficients might change. Okay. And then you continue this switching indefinitely. So you keep switching from one to the other. So the question is, what happens as time goes to infinity? Okay. So to make it even more interesting, let's assume that, remember, in each environment, when the environment is fixed, we know that the competitive exclusion principle holds. So it's impossible for both species to coexist if there's no switch. So let's assume that in environment one, the trajectories look like this, right? Everything converges to the x1 axis. So x1 is the dominant one, x2 goes extinct. Let's assume that in the other environment, the same thing happens. The same species, x2 goes extinct and x1 persists. So in both environments, the same species is surviving and the other species is driven to extinction. Right? Now the question is, what happens if we start switching? Well, our intuition is that nothing should happen because the same species is dominant in both. However, that's not what the math says. So if you suitably choose the waiting times, T1 and T2, so everything else is fixed. I showed you the trajectories. So the deterministic dynamics in each environment is fixed. All you can change is how long you spend in each environment. Well, if you choose the rate suitably, you can show that competitive exclusion principle fails. So both of them could persist. So Hutchinson was right, and by spending time in different environments, there can be something like a rescue thing, even though it's counterintuitive. But actually, we're able to show, this was quite a while ago, that you can have 4 different regimes. Remember, in both environments, x1 persists and x2 goes extinct. So you have 4 different regimes based on the switching rates or the waiting times. The first one is nothing changes. This is what our intuition was telling us, right? X1 is still the one persisting, x2 goes extinct. Second regime is both of them persist. Now, the third one is the least intuitive because you get the complete reversal of what you expect. X1, the one which dominates in both environments, now dies, and x2 persists. And finally, you get something like bistability, depending on your initial conditions. With a certain probability, you get that x1 persists and x2 goes extinct. And with 1 minus that probability, you get the opposite. Okay, so this is what happens, but now I'll try to explain, again, based on those invasion rates, which I told you about in the SE setting, how you can get these things. I mean, question is, how can we get something like this? Okay, so the general framework is the one of piecewise deterministic Markov processes, where you just follow the flow given by some ordinary differential equation for a random time, then your environmental state changes, and you follow the dynamics given by a different ODE for a random time, and then you keep switching like this. So you have finitely many. You assume that you have finitely many environments, and each one comes with its own dynamics, right? And then you can switch between. So little r keeps track of the environment, which will be from 1 to capital N. So if at some time t we know what environment we're in, it means we know what ODE we follow there. So that's why the dynamics is captured by this. So it still looks like ordinary differential equations, but now Fi, the vector field or the per capita growth rate, if you want, depends on the environment. So if you have a different environment, you have a different Fi, different interaction, right? How does R change? Well, you can make R very fancy. You can say that R switches the switching rate between if you know that you're in state I, what's the probability that in a small time you jump to state J? Well, it will be given by these transition rates, QIG. And if you, I mean, we can even assume that the transition rates depend on the densities, but then you cannot compute anything. So the theory works, but you'll never be able to compute anything. So the simplest setting is when these transition rates are just constants, and then we get what we had in that example with 2 species. So you just have a Markov chain, which switches between n states. And then in each state, it stays exactly an exponential times. So what's the theory? Well, like once again, we have to look at the invariant measures. Now we have to keep track both of the abundances or the densities of the species and of the environment. So now the process is X comma R. So that's why the invariant measures won't just live on the exterior, so where something is extinct, but we also have to cross it with the finitely many states we have for the environment. Okay, and then you can look at the extreme points of the invariant measures, or the building blocks, if you want. Those will be the ergodic invariant measures. So any invariant measure you can write as convex combination of the ergodic ones. Okay, so once again, something very similar to what I told you in the ST setting happens. Namely, if your process spends a long time close to the boundary, and there is some kind of invariant measure or ergodic measure on the boundary, it will get repelled or attracted according to this, the Lyapunov exponent or invasion. So what do we do here? Well, we just take the growth rate, Fix, okay, and then we average it. But now we have to do two types of averaging. We have to average the integral average over the species density, and then the sum you have to average over the finitely many environments. But the idea, the intuition is the same. Get close to the boundary, you want to know if you're attracted or pushed away. Okay, so the intuition is if you have some ergodic measure mu living on the boundary, it describes a subcommunity of species where at least one species is extinct. So mu describes some type of equilibrium state of a certain subcommunity, just like before when we had stochastic differentiation. Okay, so just like in that setting, what's the condition for persistence? Whenever you get close to the boundary, you get pushed away. So at least one of these Lyapunov exponents is positive. Then you cannot converge to the boundary. Meaning that at least one of these mu's is a repellent. It repels you in one direction. Okay, and then this, I already told you what the stochastically persistent means. This is what I was saying. This is what it means that with high probability you're bounded away from extinction. Okay, and if you add some conditions, you can prove that not only don't things go extinct, but they actually converge to some random equilibrium. Okay, now let me tell you about the general extinction result. So we have a subcommunity here of just two species, X1 and X2, and their equilibrium, their random equilibrium, is given by this ergodic measure mu1, 2. And now we want to classify this ergodic measure. We want to see if it tends to attract or repel. Well, whenever you live inside the ergodic measures, right? So species 1 and 2 live inside this ergodic measure, this measure. The invasion rates there are 0, because if you live inside this random cloud, if you want, you don't tend to get pushed away towards the boundary or blow up to infinity. So these internal invasion rates will always be 0. The only thing that matters is if someone who's not there yet gets pushed away or not, right? So the only non-zero invasion rate is the one of species 3. So we call mu1 a transversal attractor if this invasion rate is negative. Now, and so I sub mu will denote the species which live inside the support. R mu is the subspace which contains the system. Okay, so now I can draw in n dimensions, but it's just the same idea. That transversal attractor is something where every other species which doesn't live there cannot invade, it dies out. If you want to, if you want to add something to this subcommunity, has a negative invasion rate, but nothing else can invade. Okay, so that's why we call it a transversal attractor. So mu attracts in all directions that are not among the directions of its support. And M sub 1 will denote all these attractors. Okay, so now we have the first extinction result just tells us if there is one attractor on the boundary, and you can get close to it, right? The thing is, with this type of dynamics, it might be the case that you never get close. It can be very degenerate. You might never get close to the boundary. So if you can never get close to this attractor, it doesn't matter that it attracts you because you're never close to it, so you don't feel its effect. However, so it's this technical thing, we call it weakly accessible. So if you can get close to the attractor, then you will converge to the boundary. Right? So it's enough to have one attractor on the boundary, then it's impossible for the species to coexist. So this here just means that as time goes to infinity, the distance between the process and the boundary will look like e to the minus alpha t. So it will converge to zero, the distance. But it doesn't. This result doesn't tell us which species go extinct. It just tells us something will go extinct. Okay, so we want a result which tells us exactly what goes extinct and what persists. So here, remember M1 denotes the attractors, and then we need a technical assumption which says that if something is not an attractor, it has to be a repeller. So you don't want to have something on the boundary where the invasion rates are zero, the external invasion rates. And that's the limit case. So it would be like linearizing around the fixed point and having the first derivative zero. You don't want that. And then you'd have to go to a higher point. Okay, so this is the general result. It looks complicated, but what it says is whenever you have an attractor mu on the boundary and you can get close to it, with a positive probability, you will converge to that attractor. So if you have multiple attractors, what can happen is, well, you converge to one of these. So this just means here, depending on your starting position, the probability might change. If you start very close to one attractor, the probability might be very close to one that you converge to that. But otherwise, if you have 10 attractors, if they're accessible, so if you can get close to them, with strictly positive probability, you converge to the attractor. And if you sum up all the probabilities, you get one. So that's everything that can happen is you converge to one of these subcommunities on the boundary. And this gives us a complete characterization, right? Because if we converge to an attractor, we know exactly which species persist, the ones supported by the attractor, and the other ones go extinct, right? So now let's go back to our toy example and see how that competitive exclusion principle gets violated, right? We have two species, X1 and X2. They compete with each other, and the coefficients now depend on the state space, the environmental state, sorry, R, and little r is just an irreducible Markov chain which switches between state 1 and 2. It just switches between 1 and 2. Okay, if it's irreducible, it will have a stationary distribution, mu1, mu2. It just says that on average, long term, it spends the fraction of the time mu1 in environment 1, mu2 in environment 2. Okay, so how do we apply this seemingly very complicated theory? We always start with the simplest subcommunity where everything is dead. Right? So we always start with the Dirac mass at 0. Now I'm cheating a bit because remember we have to keep track of the environment. So it's the Dirac mass at 0 crossed with the stationary distribution. In any case, it's trivial to compute things with the Dirac mass. So you just get that the invasion rate of species 1 into the empty community is what? It's just an average according to the growth rate in environment 1, the amount of time spent in environment 1, plus the growth rate in environment 2. Anyway, so it's trivial to compute at least these, right? If those invasion rates are positive, it means species 1 persists on its own. So there will be a stationary distribution on this axis. And if this one's positive, it means there's a stationary distribution on the other axis. So it means in isolation, if there's no interaction between the two species, each one can survive, right? And then what we have to look at, well, so there's an invariant measure here, an invariant measure here. Now we have to look at the invasion rate of species 2 into mu1, the invasion rate of species 1 into mu2, and see whether they're positive or not. So you can still compute these things explicitly, to trust me. I didn't put the formulas because they're even computing these explicitly. It's non-trivial and they involve some special functions, but you can compute them. Remember, these will always be zero, so these are not interesting. Right? Mu1, lambda 1 of mu1 and lambda 2 of mu2, there's zero. Okay, then if both of these are positive, it means, what does it mean? It means whenever we get close to this one, we get repelled in that direction. Whenever we get close to this boundary, we get repelled in that direction. So we cannot converge, right? So then there's an equilibrium. And actually, that's how you get the 4 different regimes. They're fully determined by the signs of these invasion rates. If an invasion rate is positive and the other one's negative, it means this first one persists, this one goes extinct. If both of them are positive, it means both persist. You get a reversal when this invasion rate is negative and this one's positive. And if both are negative, if both are negative, it just means that if you start here, you get attracted both by this one and by this one. So with a certain probability you converge here, and with 1 minus that probability you converge here. But that probability might change. So for example, if you start here, it's a much higher probability to converge to this one than go all the way. So that's how you get the 4 different regimes. And of course, I didn't show you, but you can show it's possible algebraically to get all these signs, right? So there's actually, you have to do some work to show that it's possible. So the summary is, well, what we try to prove? Well, we wanted to show that there's a rigorous foundation to a very general theory of coexistence. And along the way, we were able to prove conjectures of Chesson and Ellner, but also that conjecture from dynamical systems of Palis. So future research directions would be to, for example, you can include the effects of evolution, space, right? Everything we did here didn't take into account spatial dynamics or spatial spread, spatial heterogeneities. And then we also didn't take into account seasonal effects. I mean, when I first told you the story is that we have summer and winter. Of course, you'll never model summer and winter as an exponential where the season could be 0. And then many of these results can be also applied to epidemiological models, right? So because the dynamics is similar in a way. So I think many of these results can be applied in that setting as well. So that's it. Thank you very much for your attention.